Hey everyone, in this video I'm going to do some more worked questions on the P-block elements, and these are for lecture 7, so this is the second set of questions we've had on the P-block elements. So the first question of this second batch of questions is question 12, and we're asked here about the oxidation states, or average oxidation states of sulfur in two ions, so the thiosulfate ion and the tetrathionate ions. And these are important ions because they're involved in quite a common titration that uses iodine as well as an indicator. So let's start with the thiosulfate ion, although the way we work them out is both the same. So if you remember some of the rules for calculating an oxidation state, if it's a polyatomic ion such as these, the sum of the oxidation states is equal to the charge on the ion. So in this case it's a 2- anion, so we're looking for the sum of the oxidation states to be -2. Now, the best way to start is with the oxygens. We know that except in some really exceptional circumstances, oxygen contributes -2 to an oxidation state. In this case, it is just as normal. I mean, oxygen's the more electronegative of the elements, therefore, it's going to be in its -2 oxidation state. And there are 3 of them, so we know the total contribution from oxygen is 3 times the -2, and that equals -6. So when we're at -6, we need to get to -2. So that's the difference of 4. And the sulfur, or both the sulfurs, contribute in total +4 to the oxidation state. There's 2 of them, so +4 divided by 2 equals 2. So the average oxidation state of sulfur in the thiosulfate anion is 2. Now we can do exactly the same with the tetrathionate ion. In this case, we also want it to get to -2 because that's the charge on the ion. There are 6 oxygens. Again, each of them are contributing -2. So in total, the contribution to the oxidation state from oxygen is -12. So that means if we're at -12, we want to get to -2, the contribution from sulfur has to be 10. And this is where it's sort of like might throw you off and you might not believe it. But yeah, there are 4 sulfurs, so the average oxidation state is 10 divided by 4, and this equals 2.5. Now again, it seems the book loves putting these half oxidation states in. That's why it specifically asks for the average oxidation state. As I've said all the way through, half oxidation states can't really happen. I mean, oxidation is loss of an electron. You can't lose half an electron to get half an oxidation state. And that's where this average comes into it. This isn't necessary for answering the question, but I thought it would be nice to show why we can get these half oxidation states sometimes. So if I draw out the structure of the tetrathionate ion, you end up with 4 sulfurs, and then on these 2 N sulfurs, that's where the oxygens are. And it looks like this. So this is one of the minus charges. And here's the second minus charge. So this is where the 2 minus comes from. There are 2 oxygens that are only singly bonded with a minus. So we can actually work out the formula oxidation state of each individual sulfur, and then we'll see why they average 2.5. So why it is that these middle 2 sulfurs, their oxidation state is actually 0. So in the same way that elements such as N2, like elements in their free state, are 0, when we look in a large polyatomic molecule like this, any elements that are only bonded to themselves also have an oxidation state of 0, because the electrons are like perfectly shared between these 2. There's no giving and taking as such. Now if we look at these 2 sulfurs on the edge, I'll only explain it for one because they're identical, so the same applies to the other. But here the bonds are uneven, like they're not the same element, so one of them is more electronegative than the other, and we can say that that takes all of the electrons. So this sulfur has 5 bonds to oxygens, so it's got 2 to this oxygen, 2 to this oxygen, and 1 to this oxygen. And we can pretend that because oxygen is more electronegative, it's taking all of the electrons from those bonds, all the sulfur given electrons. So there are 5 bonds around here, which means that the sulfur has actually lost 5 electrons. And yeah, if you lose an electron, you get oxidized, so it's a plus oxidation state. Bit confusing sometimes. So yeah, that's why this sulfur, and then likewise the equivalent sulfur on the other end, is also in a +5 oxidation state, because it's lost 5 electrons, two to this oxygen, 1 per bond, 2 to this oxygen, 1 per bond, and 1 to this oxygen because of this bond. So yeah, that's why you can get half oxidation states when we work out the average like this. In reality, there are no half oxidation states. We've got 2 plus 5 oxidation state sulfurs and 2 in the oxidation state of 0. But when we average it across the whole molecule, that's how we end up with half oxidation states. Again, you don't really need to be able to show this for the exam, but I think it is really helpful. The answers keep coming up with half oxidation states, so it's nice if you can see an example of why and how to work it out if you're really interested. So in question 13, we're looking at the bond angle between OF2 and H2O and why they're slightly different despite having the same shape. So let's draw them out and we can start the explanation from there. So on this side I'll draw OF2. Oh, no, it doesn't need the 2, we've already got the same one. So yeah, OF2 is the bent geometry, as is water, which we'll draw here. So yeah, they both look at the moment exactly the same. So we can put on the lone pairs of oxygen there. So that's why it has this bent configuration. It's got 4 electron pairs around it. So it has a tetrahedral shape. But then because 2 of them are lone pairs, it has this bent geometry. Exactly the same reason for the OF2. In this case though, fluorine has a couple of lone pairs itself, or 3 lone pairs itself even. There we go. So yeah, the bond angle of OF2, so that's this angle here, is 103.1 degrees. It doesn't say in the question, but the water is 104.5 degrees. So then the question is, yeah, well, why is the bond angle of OF2 a little bit smaller than H2O? Well, this all has to do with where the electron density is, which is exactly related to what happens with the electronegativity. So let's start with water first. Water's got this bond angle of 104.5. And if you think of the electronegativity, in this case, the OH bond, oxygen's the more electronegative part of the bond, the more electronegative atom. Therefore, the electron density is really going to be more towards the oxygen, and the same on this bond. So you've got quite a region of electron density here around the O, and that's going to be repelling each other around here. So if we can almost pretend the bonding pairs are like, wrong colour, here and here. These bonding pairs are going to repel each other quite a bit. So that sort of like forces the bond open a bit more. So that's why it has this angle of 104.5. If we look at the electron density on the oxygen, the OF2 molecule instead, in this case, fluorine is the more electronegative element. So the electron density here is actually more towards the fluorine end of the bond, and yeah, will be much wider apart because they're further apart from the centre. So then if we say the bonding pairs are kind of here, they're really not going to be repelling each other so much because they're not sort of concentrated towards one central atom. They're more spread apart, and because they're further apart, the bond can actually be closer together, and these electron pairs still won't repel as much. So it's all to do with the electronegativity and therefore the electron density, giving the bonding pairs a bit more space to move in the case of OF2 than H2O. Question 14 is another one calculating the enthalpy change of formation for a reaction or for a certain molecule, but this time we're doing it just from bond enthalpies. So there's a slightly different way to do it, but we'll start the same way as always and write a balanced equation for what's going on. So we want to form Cl2O from Cl and O. So chlorine is present as an element as Cl2, so we're taking chlorine and oxygen, which in its elemental form is O2, and that's forming Cl2O. 2O. And then this is what we want to work out, the enthalpy of formation for this Cl2O. Now let's balance it first. It isn't done yet. We've got 2 oxygens on the left and 1 on the right. So let's go put a 2 in front of the products. So we've got our 2 oxygens then, but we've got 4 chlorines. So we're going to have to put 2 in front of here. And then everything is very happy. So now that we've got our balanced equation, oh no, one thing isn't balanced. Now that we're making 2 Cl2Os, this is actually 2 times the delta H of formation, which will come in very important at the very last step of what we do. So when we're working out the enthalpy change of formation for bond enthalpies, it's quite simple. The delta H F is essentially the sum of all the bonds broken minus the sum of all the bonds made. This is some dreadful handwriting. Yeah, so all of the bonds broken minus all of the bonds made. So let's see what we're breaking now. We've got, as the bonds broken, we've got 2 Cl bonds getting broken and 1 oxygen bond, double bond, being broken. And then on the bonds being made, each Cl2O molecule has 2 ClO bonds, but we're making 2 of the molecules, so we've actually got 4 ClO bonds being made. So that'll then equal 2 times 242 plus, let's give some big brackets here. 2 times 242 plus 498, and that's the sum of all the bonds being broken. And we want to take away 4 times 205. So this works out to be 982. This one is 820. So then what we've made is 162 kilojoules per mole for the delta H formation. But as I said at the beginning, this is for 2 delta H formations because we're making 2 molecules of Cl2O. So we've actually got to divide this by 2 to get our very final answer, which means the delta H of formation for Cl2O is 81 kilojoules per mole. Now, the second bit of the question asks, would you be able to expect this? Would you be able to expect to prepare this from the elements? And the answer is no. It's endothermic, and yeah, it's not stable with respect to the elements. Like, it would much prefer to be chlorine and oxygen than together in this molecule of Cl2O. So question 15 is another calculate the enthalpy change for such a process sort of questions. So this time we're looking at a disproportionation of IF to IF5 and I2. So let's write out the equation, then we can balance it and work it out. So IF goes to IF5 and I2. And if we look at the oxidation states of iodine in these 3 molecules, then we'll see that it's a disproportionation reaction. If you remember, that's when the element at the beginning of the reaction changes to be in 2 forms, one with a higher oxidation state and one with a lower. So the oxidation state of iodine in IF is +1, and then it goes to make IF5, which is +5, higher oxidation state, and I2, which is 0, as all elements in the free element state are, which is a lower oxidation state. So yeah, it's a disproportionation reaction, and the enthalpy change of disproportionation here is what we're looking at. So first we need to balance it. It's clearly not balanced. On this side we've just got an I and an F, and here we've got 5 Fs and 3 Is. So let's go ahead and put 5 in front of this, because then we've got 5 fluorines on both sides. We've only got 3 Is on this side, so we're 1 short. So let's put 2 in front of this. And now, yeah, we've got 5 Is and Fs on this side, and 5 Is and 5 Fs on this side. Now, there are only 2 steps in this. We just break some bonds and then make some bonds. So first we're going to break up IF into 5 Is and 5 Fs. Oh, computer notification. And yeah, the breaking of it is just the opposite of the forming of it. So then the enthalpy change is minus the enthalpy change of formation for IF. Because yeah, the breaking down is exactly the opposite of the forming. And then we need to do the making of the other molecule, the IF5. So we take these and we form the IF5 molecule. So this is just the delta H of formation of IF5. This time, it's only one because the stoichiometry here. Oh, let's do the stoichiometry for both of them. Actually, start over this side. So we've got 5 in front of the IF. We need to break up 5 of them. So this will be minus 5 times the enthalpy change of formation of IF. Over this side, there's nothing written there. It's a 1. So then we do just need to do this times 1. So let's write out a whole equation for working this out. We've got the enthalpy change of disproportionation equals minus 5 times the enthalpy change of formation of IF plus the enthalpy change of formation of IF5. Now if we put some numbers in, so this first one is minus 5 times minus 95, and then here we've got plus the enthalpy change of formation, which is minus 840. I've got enough room to do this a little shorter. So minus 5 times minus 95 is 475. Plus minus is a minus 840. So this gives us an enthalpy change of disproportionation of minus 365 kilojoules per mole. And that's exactly that. In question 16, we're given some reactions or some chemicals reacting with each other. We're asked to predict what the products are going to be and write a balanced equation for the reaction. So the first one, part A, is with a xenon difluoride and arsenic pentafluoride. So if you remember to the last 2 videos actually, where we were looking at group 17 and group 18, arsenic pentafluoride turned up in both of them, and that's because this is a fluoride ion acceptor. So it will end up making an ion pair where this takes a fluoride ion. So what happens here, we get xenon difluoride plus arsenic pentafluoride, and this goes to xenon monofluoride plus, because it's lost that fluoride anion, and the arsenic then becomes a hexafluoride anion. The next one, Bi3 plus ammonia. This is usually if you see something with Bi3, BH3, there's actually an exception down the bottom, but usually these are sort of Lewis acid, Lewis base reactions. So in this case we've got Bi3 plus ammonia. So remember, the Bi3 is electron deficient. It's only got 6 electrons in the valence shell of the boron, therefore it's going to act as a Lewis acid. The ammonia has a lone pair, so it's going to act as a Lewis base and donate that electron pair. So then we end up, and we can write it this way, I3B NH3 with an arrow showing the way that the electrons are being coordinated from the ammonia to the boron. The next one is of a phosphorus oxide reacting with water, and these the reactions of all the phosphorus oxides with water create acids. That was one of the trends we saw in the periodic table, is that the non-metal oxides tend to be acidic, therefore if they react with water they'll form an acid. So we'll go for P4O10 plus water, and the common acid of phosphorus, although it's not the only one, is phosphoric acid with the H3PO4 formula. Now we do need to balance this a bit. You can see we've got 4 phosphoruses on the left and only 1 on the right, so let's go put a 4 here, and then we also need to balance all the hydrogens and oxygens. that we've created. So a 6 here should leave us with 12 hydrogens. Yeah, 12 hydrogens. That is all balanced nicely. Now the final one is SF4 plus BF3. Now this is, a slight trick. The first time you see it, exactly what I was saying in part B, if you see BF3, it's usually acting as a Lewis acid because it's got that empty p orbital. This time when it's with SF4, it's actually acting as a fluoride anion acceptor, much like the arsenic pentafluoride is actually. So this is a very similar reaction to the one we saw at the top. SF4 plus BF3 goes to make this ionic compound where we've got a SF3 plus that's lost a fluoride ion, and BF4 minus because it's acted as a fluoride ion acceptor. The BF3 has now got an extra fluoride anion. So yeah, that's how to balance all of those. And these are typical sort of behaviours to know of the P block compounds. Finally, question 18 is using VSEPR theory to predict the shapes of some molecules or ions. This time it's a bit harder than when we looked at VSEPR in the revision lecture, lecture 1. This time we've got double bonds to deal with and also some hypervalent molecules. So I'll start with a couple of notes. So the first one is hypervalency. You don't need to know why hypervalency occurs for this course, but if you are interested in it, it's quite complex. You can't understand it just by thinking of extra orbitals are involved in the lower periods. You actually have to use molecular orbital theory to give the best idea of how it's possible without getting things like the d orbitals involved. And they've got a little explanation of that on page 249 to 250 using xenon difluoride, I think it is. It's an example. So you don't have to know it for the course, but if you are interested in why hypervalency can happen in the second and third periods and lower, then check out that bit on those pages. The second one I wanted to start before we actually get into these examples is that to do VSEPR, we need to start with the Lewis structure and know how many bonding pairs and lone pairs there are. So I thought I'd share quickly some of my hints and tips that I use in my head when I'm drawing Lewis structures, because it makes it a bit easier. There's always also these the things in the textbook, like I'll draw circles, make as many bonds as you can, but I've got some rules that kind of work all the time to help draw them quicker and without having to think so much. Each element has a certain number of bonds it likes to have. So I'll write them down the right hand side and we can refer back to them as we make the Lewis structures. The first one, hydrogen likes to have 1 bond. Carbon then likes to have 4. Let's go nitrogen first actually, so we're down in numbers. Nitrogen likes 3 bonds, oxygen likes 2 bonds, and fluorine likes 1 bond. And this is, we kind of saw it actually when we were doing the proper big Lewis structures, if you remember, like with O and showing the valence shell with all the electrons. This has 6 valence electrons. So when we did O2, it showed that oxygen likes to double bond to itself when it makes O2. N2 made triple bonds. It's essentially because of how many unpaired electrons there are in this valence shell. So if you see oxygen has 6, it needs to form 2 bonds to completely fill this octet. So for the first row, this is pretty hard and fast. They like to make 4, 3, 2 or 1 bonds. Now if you do make, we'll see examples where we don't actually fulfill this. If you have 1 less than this, 1 less equals an anion, so a negative charge, and if you've got 1 more, you get a cation. So for example, if you had nitrogen with 4 bonds around it, it would be nitrogen with a plus on it. Oxygen with only a single bond is a minus anion. So they're sort of the rules we can use while we're when we're making all of these to help make our lives a little bit easier when it comes to the Lewis structures. So let's start with IF5. So we've got I as the central atom, and we know that fluorine likes to make just 1 bond, a single bond. So we can draw 5 fluorines around it like this. There we go. Next, we need to know how many lone pairs there are. So if we think of how many valence electrons iodine has, just as an element, so it's in group 17, it has seven valence electrons. You can see 5 of them are already participating in covalent bonds. So you've got 1, 2, 3, 4, 5. So that leaves 2 valence electrons that aren't being used for bonding. So there must be 1 lone pair. So then we've got 6 electron pairs in total and 1 lone pair. So 6 electron pairs means that we have the octahedral geometry, and then because we've got 1 lone pair, then the actual structure ends up being square pyramidal, which I'll put in this very abbreviated form here. And if you need that table from the textbook to remember what sort of shapes there are, that is on page 230. So this is the one that has the big table, and it says how many what the geometry is, so like how many electron pairs around it, and then how that geometry changes depending on how many lone pairs there are. So the next one, I'll get rid of this so we've got a bit more room to work with. The next one is xenon pentafluoride. So we've got xenon in the middle. Again, fluorine just like single bonds, so let's draw some single bonds around it. And then working out the lone pairs again. So xenon is a noble gas. It's got a complete octet already, actually. It's got 8 valence electrons. So 4 of these valence electrons are being used in the bonding here. So that means it's got 4 electrons that's just chilling in pairs. So that's 2 lone pairs. We'll say 1 on top, 1 below. So then we have a similar thing. We've got 6 electron pairs even, but 2 lone pairs. And if you look up that table again on page 230, then we end up with the square planar geometry. And as I say, this is a good example of hypervalency. Like xenon already has a complete octet, but it's expanded that. And it's the example of xenon difluoride rather than tetrafluoride they use on page 249 to 250 to explain hypervalency using the molecular orbitals, which is nice. Next up, we start dealing with double bonds and ions. So IO3 minus, iodine is the central atom. And then this time I want to put 3 oxygens around it that has 1 negative charge. So if you remember, oxygen likes having 2 bonds to it. Since oxygen isn't a central atom in the way that it would be in like water or something, say, iodine's the central atom. Then we're just going to put double bonds to the oxygens. So we have a double bond to this oxygen, a double bond to this oxygen, say, and then we've got a negative charge. So we know that one of these oxygens only actually has a single bond. So we can do it like this, O minus. Next, we have to work out how many lone pairs there are again. So iodine, as we said before, has 7 valence electrons. It's 1 for each of the bonds. So this double bond is 2 electrons from iodine, 1 from iodine, and 1 for each of them there. So it's 5 of the valence electrons used in bonding. So it again has 1 lone pair. Now's where it gets tricky when we look at electron pairs and double bonds in particular. So for the case of working out how many electron pairs in total are around it, we don't actually look at the sort of pi bond. So we're just looking at the sigma bond. So we can actually count this double bond. Oh, sorry, I'll get the highlighter out. This double bond doesn't count as 2 electron pairs. We actually just have to pretend it's 1, as it would be, like, say, in a single bond. So in this case, it's actually got 1 electron pair here, 1 electron pair here, 1 here, and 1 here for the lone pair. So each of the double bonds, only contributes the same amount of electron pairs to VSEPR theory as a single bond. So we've got 4 electron pairs in this case, and 1 lone pair. So it's got 4 electron pairs. It starts at the tetrahedral geometry, and then we've got 1 lone pair, so that makes it trigonal pyramidal. Trigonal pyramidal. It might have made up shorthand. Next up, we've got a POCl3. So this one again, we've got some double bonds and some hypervalency. We've got a bit of everything going on. So let's start with phosphorus as the central atom. And then oxygen, as we said, likes to have a double bond. So we can put a double bond here. Ooh. And 3 chlorines. So we can just dot them around. Now, chlorine is, the same as all the halogens. So it has only 7 out of its 8. So if it wants to make a bond with something, it can just make a single bond. That satisfies its octet by having 1 bond. But much like fluorine. But then things like chlorine, bromine and iodine, they can go hypervalent. But it depends, It will be if chlorine was a central atom, like in chlorine trifluoride, say, then it would expand its octet. But if it's just there, as something bonded to the central atom, it's just going to form a single bond. So we've just got 3 chlorines like that. Now we do this same thing again, work out how many lone pairs are on the phosphorus. Phosphorus is in group 15, just below nitrogen, so that means it has 5 valence electrons. So we can see the ones that's contributed to bonding, it's 1, 2, 3, 4, 5. So it's actually, all its valence electrons are already in use making bonds. Now again, we have to work out how many electron pairs in total there are. So we've got 3 single bonds and a double bond. Remember, a double bond just counts as 1 electron pair again, because we only take into account the sigma contribution for VSEPR. So this is 4 electron pairs and no lone pairs. So this is in the tetrahedral geometry because of the 4 electron pairs, and it's tetrahedral because of the no lone pairs. But one thing to be aware of is that because of this double bond, because they're not all single bonds, there isn't a perfect tetrahedron as we'd usually imagine it, say something like CH4 was. Because of this double bond, it's actually a distorted tetrahedra. So this is like a particularly tricky example. BF3, if you remember when we did the lecture on, or the video on group 17, we were talking about interhalogen compounds, and this is an example of one. I said they're really good because they fit VSEPR theory very nicely. They also, especially if you've got halogen bonding to a halogen in any way, they always just do single bonds. You're not going to find like a iodine fluorine double bond in any way. So we've got a bromine in the middle, like that, and then we just need to put 3 fluorines around it. So F, 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 and then work out the lone pairs again. So bromine, group 17, 7 valence electrons, 1, 2, 3 being used in bonding, so it's got 4 electrons in pairs, so 2 lone pairs. So if we look at that, there's 5 electron pairs this time, from 1, 2, 3 from the bonding and 2 from the electron pairs, and 2 lone pairs. So 5 electron pairs means it has a trigonal bipyramidal geometry. Then it's got 2 lone pairs, which means the actual structure is T-shaped. That one I'm not going to abbreviate. And finally, we've got this xenon dioxide difluoride thing. So again, xenon in the middle. Oxygen likes to make 2 bonds. So we'll give them double bonds. I'm going to run out of room. There we go. And fluorine just like single bonds, so let's just give that a single bond. And then let's work out how many lone pairs are on the xenon. So it's got 8 because it's in group 18. 1, 2, 3, 4, 5, 6 are involved in bonding already. So it has 1 lone pair. So how many electron pairs is this? Well, we've got double bonds, remember, contribute just 1 as well. So we've got 1, 2, 3, 4 from the bonding and 5, a fifth from the lone pair. So we've got 5 electron pairs. So it's going to be based on the trigonal pyramidal geometry again. This time we've got 1 lone pair. So that one then makes a disphernoidal structure. So quite a long explanation for this question, but I do hope it helped.